Coulomb's law, stated by Charles Coulomb, a French physicist, to find the electrostatic force of attraction and repulsion between two charged particles. This law was defined after an extensive study of force between the charges using a torsion balance. A torsion balance has an insulating rod with a metal-coated ball at one end and a balancing sphere at the other. This rod is suspended with the help of a suspension fiber. The graded circular scale gives a measure of the displacement of the sphere due to repulsion. Another static sphere, which is identical in size to the metal-coated ball, is placed at the zero mark. A micrometer screw at the top helps adjust the distance between the free and rotating spheres. The static sphere is first given a charge Q by bringing a charged object in contact with it. Then, the rotating sphere is brought in contact with the static sphere using the micrometer screw. Due to conduction, the charged static sphere now loses half of its charge, that is, Q by 2 to the other sphere. This happens because the two metal spheres are identical in size. Now, both the spheres are identically charged, with a charge of Q by 2 each. They start repelling each other since like charges repel. The measure of repulsion is the amount of deflection or the angle through which the sphere attached to the rod is displaced. The static sphere is now discharged by grounding. To recharge the static sphere, the rotating sphere is brought in contact with the static sphere using the micrometer screw. Again, due to conduction, the spheres now have a charge Q by 4 each. As both the spheres are identically charged, they repel each other. However, the angle of deflection observed is lesser than the previous observation for charge Q by 2 on each sphere. Therefore, it can be concluded that as the charge on the spheres decreases, the force of repulsion between them also decreases. From these experiments with charged spheres at constant distances, it was concluded that the electrostatic force between two charges is directly proportional to the product of the charges. If the charges are Q1 and Q2, then electrostatic force F between them is proportional to Q1 into Q2. Let this be equation 1. Now, keeping the charge on each sphere constant, if the distance between the charged spheres is varied using the micrometer screw, the angle of deflection is found to be inversely proportional to the square of the distance r between the charges. Since the force of repulsion is proportional to the angle of deflection, we can say that the electrostatic force F between the charges Q1 and Q2 is inversely proportional to the square of the distance r between the charges. Let this be equation 2. Thus, according to Coulomb's law, the electrostatic force between two charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between the charges. Hence, the electrostatic force F between charges Q1 and Q2 separated by a distance r is proportional to Q1 Q2 by r square. Let this be equation 3. A constant of proportionality K is used to get the equation F is equal to K Q1 Q2 by r square. Let this be equation 4. If the charges are separated in free space, that is, air or vacuum, the value of the constant K is equal to 1 by 4 pi epsilon naught, where epsilon naught is called permittivity of free space. Thus, the electrostatic force F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. In SI units, the value of the proportionality constant K is approximately equal to 9 into 10 power 9 Newton meter square per Coulomb square, and the value of epsilon naught is equal to 8.85 into 10 power minus 12 Coulomb square per Newton meter square. Hence, F is equal to 9 into 10 power 9 into Q1 Q2 by R square. Using Coulomb's law, a unit charge can be defined as one that experiences an electrostatic force of 9 into 10 power 9 Newton when placed at a distance of 1 meter from another unit charge in free space.